Good morning, Paris. I am here to talk about routing in Polaris. Polaris is the working code name for the next edition of Ember. This is not a talk that's about presenting a complete design to you. We still have plenty of experimentation and feedback and community work to do together to have a full design. That's why I subtitled my talk here, How to Think About Routing in Ember's Next Edition. Because really what I want to go over with you is, my big theme is going to be that we have built already so many great building blocks that become most of the raw material we need to put together a really great next router. And if we understand those building blocks really well, it's not a large gap to be able to plug together newer, better things. So here's a little map of where we're going to go in the topics today. I want to talk about routing. But to talk about routing, I have to talk about resources and lifetimes. And to talk about resources, I have to talk about reactivity and lifetimes. So we're going to start with lifetimes. And to start with lifetimes, I'm going to tell a story. I'm going to get Zoom out of my way. Okay. To start, I'm going to tell a story. It's got everything you need in a great story to start the morning. We've got some intrigue. We've got some revolution, romance, a duel to the death, mathematics. It's great. And it's set with some local history right here in our neighborhood, here in the Latin Quarter. So within a half a kilometer here of Emberfest is a pretty famous secondary school, Lycée Louis le Grand. It has like 7 Nobel Prize winners as graduates. It has many presidents of France and prime ministers and famous writers. But the graduate I want to talk about today was named... Come on, I'm having the same problem. Évariste Galois, and this is a guy who really strikes me as an angsty teen. He had a lot of anger through school. He was really brilliant, but he didn't do well in school because people didn't understand him. He was always leaping too far ahead, and people didn't appreciate his ideas. So he was also a staunch Republican under a time when France was under a king again. And for the Americans, Republican in this context means he actually likes democracy. Weird. So in July 1830, there's another revolution. He gets himself expelled from college for writing about it a little too boldly. He goes and joins a radical artillery unit of the National Guard. And these guys had enough of a reputation that the government disbanded them soon after because they were afraid they were going to overthrow everybody. At a banquet with those guys, he gave a toast to the king, to Louis Philippe, while raising a dagger above his cup, which got big cheers from the audience and got him several weeks in jail. He was eventually acquitted on that one. Soon after getting out, though, he was right back at it again. He's at the head of a protest, wearing the uniform of his now illegal military unit, armed with several pistols, a rifle, a dagger. That got him another 9 months in prison. All this, he's only 19 years old at this point. Immediately upon getting out of jail, somehow he's talked into a duel. The details remain mysterious. Nobody's exactly sure what went down and why he went into this duel. There's allusions to a broken love affair. There's conspiracy theories that his political enemies set the whole thing up to get rid of him. History's not really sure. But in any case, he gets shot, dies the next day, age 20. So if that was the whole story of him, he would just remain a kind of interesting, hot-headed minor character in this period of French history. But the night before the duel, Galois was so convinced of his impending destruction that he stayed up all night writing letters, and one of those letters founded an entire new branch of mathematics. We still call it Galois theory in his honor. In programmer terms, he refactored the foundations of a big chunk of modern mathematics, and people are still working with his abstractions. The modern meanings of terms like group and finite field all come from him. So on the left, that's the letter he was writing the night before his duel. On the right, this is a slide from a current modern algebra graduate level course with his ideas in it. So all very interesting, but how do I possibly connect this back to our topic? Well, Galois had important work to do right before destruction. And that comes up a lot in programming. Lifetime is an important general concept. We've heard a little bit about him already at the conference, but I do want to give detail just to clarify and let people think about lifetimes more generally than just one implementation, because all state in any program has a beginning and it has an end, and we call that time the lifetime of that state. The thing that makes lifetimes tricky to deal with is that those pieces of state depend on each other in complicated ways. They form graphs of dependencies, and that means their lifetimes are entangled too. And if you mess that up and you make a lifetime too short when you really needed it to be longer, you end up with a use after free bug, a crash, or your program forgets something that's still important to users. But if you end up with a lifetime too long, you end up with memory leaks or bugs where things are affecting each other that shouldn't. So every programming language and environment really needs some solution to dealing with lifetimes. Some are more explicit than others. This is an example. Rust, for example, makes lifetime an explicit syntactic thing that you have to actually label on your variables to say how their lifetimes relate to each other. The compiler will just, so Rust has a borrow checker to handle lifetimes. JavaScript, along with a lot of other popular languages, mostly uses garbage collection as the language level solution to lifetimes. So as long as you hold a reference to something, you can keep using it. And garbage collection is simple because you don't have to deal with it so directly most of the time. Until you have a memory leak or something, that's when you'd need the dev tools. This is the screenshot I'm illustrating with here is showing the Chrome dev tools, which you can learn to use to understand how the garbage collector is seeing your code. But garbage collection is too weak by itself to model a lot of important lifetimes in your application. Mostly that's because JavaScript doesn't guarantee when or if garbage collection is ever going to happen. So just because something hasn't been garbage collected yet doesn't mean it's really still being used, which is why we have API like Ember destroyable that gives us tighter bounds to mark the exact ending of when something's really needed anymore, and to figure out when it's not needed anymore through our own tracking of the hierarchy of relationships of objects. And it's a good API. It's extensible. You can make any arbitrary object participate in it. It's not just for framework provided things, although it is used for the framework provided things. So everything meshes together quite nicely. So that's the quick review of lifetimes as a concept. We're going to do an even quicker review of reactivity. And that's because Ember's solution here is already really good, I think, and everybody's already seen it. Right? We have the tracked decorator. As long as you mark something with the tracked decorator, you can continue using it completely normally, like any other value that didn't have the tracked decorator, but now your whole program's going to respond whenever that changes automatically. Really nice pattern. One of the shining favorite things that we've accomplished. Really great reactivity system. The only other thing I'll say about reactivity is that we also have the cached decorator, which you might not have used as much. It's a little newer, and you don't need it quite as often. But what this gives you is the ability to make your own code react the same way the Glimmer rendering engine does, so that it knows not to repeat work when all of the tracked things it depends on haven't changed. And with that basic capability, now you can really extend the system. You can do the same kind of things Glimmer does to write code that's only going to update when tracked things have changed. It's a very nice system. All right, so now we can move up from reactivity to resources. We heard a lot about resources yesterday at the end of the day from Yehuda. I think he had a slide a lot like this one. I think we're pretty aligned on the messaging. I think his said cleanup plus reactivity. I'm saying lifetimes plus reactivity, but that's really two ways of saying the same thing. Resources really fall out as a consequence of these two other features. You don't need a feature to do resources. You don't have to have some first-class thing in the framework. You don't have to have a library. It really is just a pattern that arises fairly naturally when you have these things. So we're going to do a quick example. This is a component. Yehuda also had a clock. It's very much the go-to example for resources. This is a clock that can run at 2 speeds. And the implementation of the component looks like this. I think it's a really nice, small, tight component. I think it has all the features you want, and it's really small and clean. Main thing you have here, right, here's our resource, our little timer. It's completely self-contained. Everything about setting it up, tearing it down, adjusting intervals and things like that is all hiding inside of there. And it can just react to changes to our variable that we've got here that we can set from our selector controls, render, and we get a value out of our resource here, timer now, that we can just use in our clock phase. So that's pretty straightforward. I want to show you now the implementation of timer. And this is a lot of code for one slide, but it's not that much code for everything it's doing. And I wanted to show it this way, mostly just to illustrate what's really going on under the hood when you have a resource. Because there's no library here, there's nothing magical or hidden. The only prerequisites you need to understand this code are the three things we're importing, which we've talked about already. We've got our Ember destroyable register destructor, we've got our cache and our track from the reactivity system. And everything else in here is, it's all primitives that you've seen. And so it's a lot of code, but you can stare at it and learn and think about how it works and realize there's nothing that much fancy going on here. Why we have two different classes? The top one here is the thing that's stable, so that when we say new timer here on this, in our consuming component, that's the value we're getting out, and we're going to have that value for the lifetime of our component. It's maintaining the stability and identity of this thing, but its job is to notice when inputs change. So like this is where we consume our inputs. Because this can consume tracked properties, and it's inside of a cached area here, that's going to cause this to rerun exactly when it needs to establish a new current timer. And then this thing can take care of the construction and destruction of setting up intervals and clearing them out again. So again, a lot of code for one slide, but my point is just to illustrate that resources are a thing we kind of already use a lot in our code without really thinking about it, because it's really just this combination of features where the system can compose as long as you've got entanglement of lifetimes and reactivity. Viewed this way, you start to realize a lot of things are resources. Helpers are resources. Here's a helper being invoked. The helper in this case is connected to its parent component the exact same way that timer was to its parent component, right? It's tied in with a register destructor. It's going to re-render when tracked properties change. They really are two sides of the same pattern. In fact, with helpers, we have a low-level API called invoke helper that lets you take a helper, particularly a helper like this one that is written as a class where it could potentially be stateful and have its own complicated life cycle, and you can invoke it from JavaScript, and what you get back looks a lot like a resource. You end up instantiating it a lot like a resource, and then consuming it a lot like a resource. So this particular example is kind of contrived. You wouldn't really need a helper like this one to do +1, especially since now we have plain functions as helpers, which is a wonderful feature that I had wanted for a long time. We now have. It's a great feature. If you did that, you can just use plain old functions for this whole thing. But if you do have stateful helpers, they can run like resources like this. So it's all resources is the point. So resource is the common interface that lets us compose all these things together. Helpers, as I said, modifiers are just resources that receive a DOM element. Components hold state and compose other resources. Services are resources shared for the lifetime of the app and your own custom resources. They're all resources. So that lets us say then, what about routes? Are routes resources? So if routes are resources and they work with this system, you would expect a pattern like this to work. This is the same kind of idea we've been showing with register destructor. In this example, we're assuming our route here, when it's constructed, we're going to add an event lister. When it's destructed, we're going to remove that listener. This seems like a pattern that should work. It should give you an event listener while you're in this route. It doesn't work the way you'd want. You can do register destructor on it, and it's not like it'll crash, and your callback will even eventually run. It's just that it won't run till the very end of the program being torn down. The lifetime of the route isn't what you'd think it would be. Well, I mean, if you know Ember a lot, you might know already what the lifetime of the route is, but it's not what it should be. Here's what you really have to do in a route to get that same behavior. Right? Routes have dedicated API that activate and deactivate hooks to do the same kind of thing. And so it's a consequence of this API being older than destroyable. Had we had destroyable when this was made, we wouldn't have had to invent activate and deactivate and give you a new thing to learn. But it's this extra thing to learn. If you want to learn about lifecycle of routes, it's all of a sudden different from the rest of the system. So let's look at the actual lifecycle of the things that happen in the router. So we're going to take a little time journey through an application as a user visits routes. If they start in the index route, they're going to have the actual route instance for index alive and the template for index alive. And then they transition to a new route. let's say they go into post index, right? So in this case, they entered a nested route, so the parent route posts and the child route post index both get created, their templates get created. Correctly, the template for the old route they left has now ended its lifetime. Incorrectly, the route for the route they have left is still alive. As they continue through the application, they're going to go now into post show. Now here, this template and route are alive for a good reason. These are still the active parent, even though their child has now changed. The child route template has ended like it should. Its route now has continued like it shouldn't. When we transition to another model on the same route, nothing happens with the lifetimes, and we're going to come back to that in a moment. And then if we leave our nested route entirely, our nested parent route here does get cleaned up correctly. The template does, the route does not. And so what would a more intuitive set of lifetimes for routes look like? I think it would look like this. I'll kind of go back and forth a couple times, right? We're taking all the routes and making them match their templates lifetimes. They wouldn't need to live beyond. If we do this, now that register destructor pattern does work. Now routes do compose with the rest of the system. And I also highlighted with the big yellow arrow there because it's a slightly more subtle distinction. But between those two models should, I think, be separate lifetimes. And this is a problem that leads to bugs all the time in applications that I see. Particularly the blue bar there with the split in it. The idea that the lifetime of the template for the route extends while you're in any number of different models on that same route. This was intentional. It was done as an optimization in Ember long ago, back when rendering was more expensive and rendering a whole new template was something to avoid. Our rendering is really fast now, and I think it leads to confusion. The symptom that you have this problem is you see people writing code in components to manually try to clean them up when models change. People add observers, they add render modifiers, and all trying to get things back into a clean state. And all that is just a symptom that the lifetime was wrong. And what you really need is just a fresh instance of the component. As a tip, if you are fighting against this kind of pattern, you can control the lifetimes of a block of template. It's kind of a known hack, but it's a consequence of the public API of the each helper. If you know how the each helper works, it has a sense of identity. And as it goes through the items that it's rendering, it cares whether they're triple equals each other. And if they are, it will reuse the block in its body. And if they're not, it will not. So this is a way to make a tiny little helper component that imposes the behavior that I'm saying I wish the router already had. This is how you can force it today. You shouldn't need to know a tip like this to get that behavior, though. That's why I'm arguing our router should do that as the default. By analogy, the router should really behave like we are modeling, even though we're running in a single page application, we are modeling behaviors that should feel like going from one page to another, one web page to another. And that comes from the programmer's perspective. That really should mean that if you're transitioning and actually clicking a link, getting fresh components is just much easier to reason about. Not in the parts of the pages that didn't really change, but in the parts that did and really got a new model. That new model, it makes sense. So we're going to make a list of our routing goals that we're discovering in this talk. So our first one on the list is make routes and their templates have useful lifetimes. Let's talk next about the differences in how you would load data in a component and a route, especially after you've already invested in resources that can do a nice job of loading all your data in a component. In this case, the example on the left is a component using a resource that knows how to load metadata about Pokemon. It's a really nice API somebody has for testing APIs that gives you all the data on all the Pokemon. Once you've invested in that infrastructure, and this is all done, this particular example was written in TypeScript with Glint, and it's fully type checked and all. Like you get back really great feedback on the resource, and you get back well-typed data, and you get feedback from Glint. It's all very nice. Once you invested in a whole bunch of good resources like that work in your components, how do you use them in your routes? It's not obvious, right? When you look at how you set up a resource, it ends up being kind of living on the instance of the component, having its own state. it's not obvious how you would want to use it. So I think we probably want to make resource routes themselves expose their data loading as a resource. So this is one possibility of how that could look. If we do this, this doesn't just improve consistency with components. It makes it easier to manage models that have their own lifecycle concerns. For example, some models care about subscribing to updates while you're looking at them. Some of them care about polling for updates. Some of them care about refreshing under certain logical conditions. All those things today really require you to learn extra API and for us to support extra API on the routing layer. And with this pattern, your resources themselves can be composed out of tools that know how to do that. If you want to have a polling-based resource, you can have that. You can make it work in a component, you can make it work in a route, and we don't need a lot of API on the route to do that. If we do this, we also do need some conventions around what that resource has on it. So, for example, in the case of the component on the far left here, right, the component has to deal with its own loading states, error states, all right there. Part of the pitch for using the router for your data loading is that when you're doing conventional things, you should get a lot of that much more for free, and we don't want to lose that. So the resource here would have to follow some conventions where the resource itself exposes what am I loading, am I errored, where's the promise that somebody could wait on if they want to wait for me to load. As long as we do that, and as long as the router itself looks for those that interface on this resource, we can still get all those things. The router can still absorb your asynchrony, it can still handle error states in a conventional way for you, etc. New routing goal, let routes expose resources to handle data loading. Along with this, we get two other much requested features, as long as we do it right. One is to eliminate the when do model hooks run confusion. If you're not familiar with this one, the model hook on a route that loads all your data, if you transition into that route via the ID, via arguments, parameters, you will run the model hook to load the model. But you can also pass an existing model to the transition to, and then the model hook doesn't run. And that's pretty much a megatroll. It's confusing. It's also why you need a before model and an after model distinct from the model hook, because those do always run and the model hook does not. So there's a lot of complexity. This idea of doing it through resources eliminates that confusion, because the resources themselves only have access to the params. Also, the lifetime change that we mentioned as the first item also helps with this, because you realize the lifetime of the route is scoped to one model, and anytime you're changing, you're getting a fresh resource. All it has access to is the params. It's got to produce a model. It would run the same each time. And if you really do want, and the reason for that behavior again was actually intended for caching. The idea was that if you already had a model, you could transition directly to it and avoid loading it again. That was the intent of that feature. But if you really want that behavior, you can still do that. You could have a resource that has that caching behavior built into it. You could use it when you need it, not when you don't, so that it's not invisibly happening and confusing you about why your code's not running. The other thing that falls out of this is allowing parallel data loading in nested routes. So today, a parent route would load its data, and it would finish before the child route would load its data, and that would finish before a grandchild route could load its data. And the reason for that is that each of those routes has synchronous access to its ancestors' models, which is very convenient to have, but it means that you're waiting for each other, even when sometimes you didn't really need to, and you could have fetched all that data in parallel. The idea here is that the routes could still have synchronous access to their ancestors' resources, but resources are constructed synchronously, so they're there right away. And then if you want something from that resource, your own resources can compose with them. You can wait for them if you need to, but not wait for them if you don't. And so you'd gain the flexibility to parallelize where that makes sense, but still enforce serialization where that makes sense, which you do want if you're, for example, having a parent route do an auth check before you're going to move on to doing other things. So that's another nice sub-goal that falls out of what we've talked about so far, I think. So if we're going to do this with resources all the way down, if our data loading is in the routes is through resources, the routes themselves, once they've got these kind of lifetimes, really, you can think of them as resources. They're getting absorbed into this we're all resources. The Borg will assimilate you, the resource Borg. So the nice thing about that is much of the implementation we need to make this new router then means it's already done, because the way you build this router is using the tools that we've already been talking about. If you know how to compose resources, you know how to use Glimmer tracking and Ember destroyable, that's the primitives to build the router itself in. So the router itself would be built as a resource controlling other resources. It would look not very different than these examples we've been showing of resources. But that does lead to the question, so what tracked state would the router itself react to? So one idea for that is to model a tracked URL. This would be pretty low-level primitive in the router, not something you'd have to necessarily interact with just to get started with Ember. But as an implementation strategy, I think it has real potential to have a simple system that people can understand. Just like we have tracked map or tracked set or tracked object as drop-in replacements for stock features that also happen to be reactive. You could do that for URL. You can have a tracked URL, and you could represent the current location of the page with a tracked URL. And now, as long as you get that primitive right, you can build a whole routing system around it with nothing other than tracked properties, getters, cached, destroyables. To get the tracked URL right, we do need to think about the remaining big boss fight of routing reform, which is query params. So query params are definitely the source of the most complexity in the current system. They got written because they were a real need, and they serve a real purpose. But the needs and APIs have shifted over our history, so there's a lot of warts. Query params can only keep their state on controllers. They're the last feature to need controllers. They are why controllers are still around. It would be great to not have to teach people about controllers. And so reforming query params is the last gateway to doing that. Query params can sometimes trigger actual route transitions and sometimes not. They sometimes append to the browser history and sometimes don't. The theme here is they're really trying to be everything to everybody, and it makes them complicated. They get implicit serialization and deserialization rules just by guessing based off of the default value if they get one. That's kind of confusing. They're sticky by default, meaning if you set a query param in some route and then you leave that route and you come back, it's going to be still set there. It's going to show up in your URL again automatically. You can scope how long that lives. By default, it's kind of forever. And the API for them lives on both controllers and routes, which is, again, historical shifts have led us to being more complicated than we want to be. So to try to reform this, we need to think about the data flow around query params, because it's not perfectly simple, and I think this is why the design around them has been tricky. Query params are an output of your program, just like some content you're rendering to the DOM. Right? Because we do want them to update automatically as your state changes. The point of them there is so that as someone's moving through your application, making choices, if they were to grab a snapshot of that URL by making a bookmark, reloading the page, sending it to a friend, we want it to accurately reflect what they've been doing. And so in that sense, query params are an output. But they also do serve as an input, because that's how you're going to reinitialize the state when somebody shows up at that URL. And so you do need them to initialize state at the start of the appropriate lifetime. And whenever the user is manually changing that URL bar, you do want those changes to come down. So the careful balance of the input and the output is the tricky thing about designing query params. It could be tempting to just force them to be one or the other, but those really don't give you what you want. Mostly our other the dynamic segments in our routes, our regular route params, are pretty much only inputs. The only way you change them is by transitioning. You don't have some field that you set and have side effects. But if you try to do that with the way people use query params, you get a bunch of undesirable behaviors. It really is nice to not force a full transition when you're just trying to reflect saving what the user is doing. Like a search term is a perfect example. If you're saving somebody's search terms as they type into a query param, you don't really want each of those keystrokes to be browser history for sure. You also don't really want, if we're going to do what I said and make the whole, if every route transition really tears down all your components and puts them back, that's the lifetime reform I just talked about, but you really wouldn't want to tear down all your components just because they typed one more character to append to the search term. So you really do want both the input and the output aspects of query params. So what if you could do a query param by taking an existing tracked property that you're already using and upgrading it to a tracked search param? Right. So the idea here is to be able to take any tracked property's piece of state and bind it into the URL by just upgrading from a tracked decorator to something else. And I chose the name tracked search param here as my example because it still says tracked because that's important. This would serve the same way the tracked decorator does. It is observable by the reactivity system. And I said search param and not query param just because that's what the actual spec calls this thing. The terms have been, both query and search have been used for this thing, but the actual on the URL class, it's called a search param. So the idea here would be that this example would create an actual sort by parameter in the URL. When this lifetime first begins for this component, this is going to set it up so that if a sort by query param exists, that's going to set the value of our tracked property. In that case, our initializer here never even runs. But if there was a query param, if there's not a query param in the URL, we are going to run our initializer here on the left side to get the initial value. Now, that kind of implementation is possible with decorators, particularly decorators as they have finally been stabilized by TC39 and moved to stage 3. They can do that sort of thing to treat this initializer as advisory and only taking place as a default, not to completely stomp on the value in this thing. And so this would work just like a regular tracked property. Once it's there, you could just set to it as much as you like, and it's going to reflect changes output. And at initialization, like I said, it's initialized from the URL, and if there's manual URL changes, they can come in and change it. So the hope here would be to give a tool that fits naturally anywhere in your component hierarchy. One of the painful things with query params being only on controllers is that you really want to use them in components a lot. And today you have to pass them down a lot. This would let you put them where you need them to be. It does mean it puts a little onus on the programmer not to collide with names on these query params. If they live in arbitrary components, now you try using this component twice on the page at the same time, and they're going to fight over that same query param. We'd have to give you a good error in that situation. To illustrate a little more of possible API around these things, this example shows that you could have an optional second argument to the query param that would give you a serialization protocol to say how does this value become a string to go into the URL or become back into the value as it comes out of the URL. And this is just a completely written by hand one to illustrate the idea how you would have an integer-based query param. Of course, this kind of serialization could come along with the library. You could import this integer thing and just call it in your code. But you could have a custom one when you needed to. This would have no built-in stickiness. I think you can solve stickiness differently if you really want memory about what was used last. That you have a couple choices. One is that the scoping of these is now really controlled the same way all the other scoping in your application is controlled. If this component's still alive, the query param is still visible in the URL. If you tear it down, it's not there anymore. It's not relevant. So that gives you a lifetime to controlling when the query param is visible and present. Basically, if it's relevant, I think it should be in the URL still. If it's not relevant, it shouldn't be in the URL still. If you do want to default where it was gone and it's coming back and you do want to default to some value, you can do that too, but that's a concern of where you're building your link or where you're building your transition to. It doesn't have to be built into the whole system to automatically have stickiness. So when you're about to transition into a place, you can use a utility that's going to check some service and ask, is there already a default setting for this thing? If there is, I will transition to that setting. So that decomposes the problem of stickiness into something you could use when you want and not when you don't. So that gives us another goal to add to our list, make simplified search params available everywhere. Along with that, I want to add 2 more goals. All right, you may have noticed all my code examples so far. We're using the first-class template syntax. We don't have that at the route level. right? We only have template files that stand alone. They can't use the new GJS format, the template tag, and so you can't easily import code into them. The main reason that you can't just take your template route files and rename them to GJS and give them imports is that that syntax is very deliberately designed to output full components, not standalone templates. And so the value you traditionally got for a route was not a full component, it was just the template part. And so it's not going to compose right if you just take your app routes hi.hbs and rename it GJS. It's not going to output the right thing. So we need to design the solution there. I don't think it's a super hard problem, and I'm not going to go into a lot of details on that because I know I'm already over time. This is already a long talk, but I think that's an important goal to make sure we remember to get that right. And that also connects to a final goal I want to list here, which is allowing code to load in parallel with the data. I know there are definitely teams here today who are already shipping to production with apps that use Embroider to split their routes, so that as they're entering a route, they're loading all of the code to render that route. All the components that are only used on that route will load as you're loading the data for that route, and that's great. It lets us scale out our applications in terms of features horizontally without slowing down the experience. You can have any number of routes, and when somebody's not visiting them, they're not paying the cost of all those new components and the libraries those components use. So this is a feature we want to make sure we really support natively in this design. We want to bring that feature to everybody for the Polaris era. And so we want to do designs that allow this. And so this may preclude some of the things that seem obvious as possibilities. For example, taking route classes and just giving them a template tag in their own body to be the route template would be kind of nice from an ergonomic perspective, but we'd have to design that carefully so that it doesn't force all of your component dependencies to be eager. Because if you think about what that would look like, you would probably be importing all of the components you're calling before you've had a chance to load the data for the route, and now you don't get the parallelism anymore. So there's design questions and trade-offs there. So my conclusion is that I hope that you see from this that you can help prototype all of this. You can help experiment, implement, give feedback, and try it. Because the building blocks are there, you don't need some kind of expertise in deep black magic internals of Ember or anything else about JavaScript. If you've internalized the lessons about resources, tracked properties, destroyables, those are all the building blocks you need to build the next router. You can build it in an Ember app out of the tools you already have. And I think that would not just be a toy or a prototype, that is how we will build this next router. So I want to encourage everybody who's interested to participate in that process, give it a go, try building your own examples using these patterns, and that's how we're going to get more people contributing, experimenting, sharing their results so that we can see it working, show everybody in the community the value of these patterns, get consensus around them, and ship it as the new default. And that is the end. So thank you.